The next topic is equations of lines. And one thing I want to point out is that there is a lot of good practice for this in your textbook, including the problems that I've listed here. But really, if you explore these different sections, 3.2, 3.7, and 3.8, there are a lot of excellent problems for you to practice in all three of those sections. So I want to start with a summary of writing the equation of a line. To write the equation of a line, we need to first of all make sure that it's a line. We want to confirm that the relationship is linear. And so that's what we'll be doing when we talk about identifying a linear pattern. We also will need to know the rate of change or slope of the line. And then once we know the slope, which if you need to, you can review topic 10, because there are a lot of different ways that we might find the slope. Once we find the slope, then we're going to use a point on the line to write the equation. So let's start by talking about how we can confirm the relationship is linear. In other words, identify that it's a linear pattern. So a line is formed when the rate of change is constant. Now in a graph, it's easy to see if something makes a line. It just looks like when you connect the dots, you get a line. In a description, like in an example of a problem, a linear pattern sounds like something where the rate of change is constant. So for example, the price per pound is always the same, or the miles per hour is always the same, or whatever your rate of change is described as always being the same or constant. Now in a table of values, linear means that as long as we're keeping our x values changing consistently, so for example here, even though the x values don't go up by ones, they're always going up by exactly the same amount, which is by twos. Linear means that the y values are always going up by adding the same number every time. So for example, if I add 3 every time, I might go 1, 4, 7, 10, 13. The key being that when I have a consistent rate of change in x, I also have a consistent rate of change in y. Whereas if the equation is not a linear relationship, I will not have that. So for example, in this case, even though x stays increasing by 2s and is a constant change by 2, the y goes up by 2, then it goes up by 1, then it goes up by 2, then it goes up by 1, for example. So this is an example where it's not linear. So that takes care of confirming that the relationship is linear. So however you do it, whether you look at a graph or it's mentioned in the question that it's linear, or we say, hey, the rate of change is always the same, or it looks like this nice consistent pattern when we have a nice consistent pattern here with addition, somehow you begin by confirming that the relationship is linear. And then the next step is to identify the rate of change or the slope. And that's going to be true regardless, anytime we write the equation of a line. So if you need to, go back now and review topic 10. So we're going to assume that you've got both of these down. And now I want to talk about how there are two methods where we can use a point on the line to write the equation. The first method applies if we do know the y-intercept. So let's suppose that somehow, and if you need to go back and review the intercepts video, you can do that. Suppose we do know the y-intercept. If I do know the y-intercept, then I'm going to use method 1. That only applies if I do know the y-intercept. So let's talk about how to use that method, and then we'll come back to this and we'll talk about how we can use a different method when we don't know the y-intercept. So if I do know the y-intercept, then it's pretty easy to write the equation of a line. If I know the slope and I know the y-intercept, then the equation of the line is always equal to y equals the slope, whatever it is, times x, and then you add the y value of the y-intercept. So in this example, the slope is 5. the y-intercept is 0, 2. So that means that the equation is y equals 5x plus 2. And let's talk about why that makes sense by filling in the table of values. But I didn't need the table of values or really any thought process much to do this. I was able to go straight from the slope and the y-intercept to my equation. So suppose I include one point that I know, which is the y-intercept. Then I should be able to remember that slope is 5 over 1, which means that as this goes up by 5, this goes up by 1, and get a few more points. And so I see here that this is, an example of some of the values that would make that equation true. If we plug them in, when we plug in 1 for x, we get y equals 5 times 1 plus 2, which is 7. When we plug in 2 for x, we get 5 times 2 plus 2 is 12, and so on. So this is all just method 1. So remember, we can only use method 1 if I'm lucky enough to know the y-intercept. But sometimes I just don't know what the y-intercept is. So if you've reviewed intercepts and you're sure that you don't know what the y-intercept is, then you're going to have to use method 2. And just make sure you do review, because there's a lot of ways that we know to find the y-intercept, and that's by far the easier way to do this if possible for you. So now we're going to assume you've got a problem. We just don't have any way of knowing what the y-intercept is at a glance in the problem, so we have to use method 2. Let's take a look at the next video.